In this lecture, we'll look at global variables in C in both general and static form. General global variables are in fact heavily frowned upon in modern design, and they're forbidden by many style sheets, but they still exist in legacy code. Static globals and their close cousin static locals are still acceptable design and thus are fairly common. A global variable is a variable declared outside of any function and shared by many functions in common. Line 5 of file1.c gives an example. You simply declare a variable on an independent line of code outside of any function, and the variable becomes the common property of all the code in the program and may be written to or read by any function. As you can see on line 9 of file1.c, and then down here on line 15 of file2.c, different functions in different files may access the same global variable. So a general global variable is a sort of common blackboard for communication between any parts of the code. Now, there are two forms of global: general, which we just described, and static. General globals are accessible to all functions in the program, but a static global is available only to those functions in the file in which it's declared. So line 6 on file1.c illustrates declaration of a static global. It's just like a general global declaration, except for the addition of the static keyword at the beginning. Now, at first glance, a general global variable seems highly convenient. Instead of the tedium of declaring and passing parameters between functions in order to communicate information, we could simply declare some suitable global variables and copy data to and from them in the caller and in the called function in order to communicate information between the two. The current state of the program would be embodied in several dozen, or maybe in larger code, perhaps several thousand global variables, and all the functions would manage this state in common. This design was in fact quite common in the 1960s and 70s, but it has fallen so far out of favor today that many modern languages forbid general global variables altogether. Although the shared pool of variables model sounds attractive at first, allowing all code in the program to modify any global variable proves to be a recipe for chaos. The different patterns of modification that may occur when functions are called in various sequences becomes too unpredictable. And there is the added concern of accidental modification. A global variable may have the same name as a function's local variable. In this case, the local variable is used instead of the global within that function. But imagine this scenario. You're working on a part of a million-line code base, and you decide you need a global variable. You give it a suitable name, let's say X. Sounds like a good name for a global. Now, somewhere else in the company is someone you've never met, working on an error handling function that's only called once in a blue moon. He's too disciplined to use a global, but he does use a local variable called X in his function. And he forgets to declare it. Now, this is a perfectly common error, and it's normally caught by the compiler. But in this case, his use of X defaults to your global and compiles just fine. And code that he meant to modify his local variable instead modifies your global X. So, once in a blue moon, due to an unpredictable call of an error handling function written by someone you've never met, your global variable gets trashed. Now, this is a small example of the danger of global variables and of why they've been discredited. In truth, you could prevent this particular error by giving unusual or specially prefixed names to globals, maybe global_X instead. But this still doesn't eliminate the case where someone deliberately modifies the global because they thought they knew what they were doing without consulting everyone else that was affected by it. You mean I wasn't supposed to set global master database to null in my error handler? It sure seemed like the right thing to do. You can think of a general global variable as having a bullseye on its forehead, walking around saying, please modify me, anyone, anytime. So don't create them, and do try to phase them out of old code that you deal with. Still, you will encounter them when dealing with old code and perhaps with old programmers. A static global variable, by contrast, presents much less danger, since the only way to access or modify it is from within the .c file in which it resides, and that's usually under 1,000 lines of code. Static globals can be safely used as a common data item by a collection of closely related functions that reside in the same file, and are worked on by an individual or a small team. And static global variables in different files may have the same name without conflict, since which variable you get is determined by what file you're in, which static global variable you get. And that leads, by the way, to question 1. If we created a general global variable for each 100 or so lines of code, then in a 1 million line code base, how many globals might we create? And how does this compare with the number of commonly used English words? And what does that imply regarding unique naming of globals? So coming back from a pause there, we'd have around 10,000 globals if we create one per 100 lines of a million-line code base. This is well above the number of commonly used English words, and it suggests that it might be hard to ensure that each global gets a unique name. Of course, a modern program avoids this by eschewing globals, at least general globals. But we'd also have 33,000 functions in a million-line code base if we assume 30 lines per function on average, and they need unique names. Modern languages solve this issue via namespaces or packages in which function names are grouped under larger names. C lacks this feature, but it's common practice to get a similar effect by standardizing on prefixes for groups of related functions, and if you're using globals, for groups of related globals. So for instance, the user interface function names in a large project might all have prefix UI, while the database functions would all have prefix DB. Different teams within the larger organization reserve prefixes for their functions, and perhaps their globals, and then they have free rein to choose the function names after the prefix without fear of conflict with other teams' differently prefixed names. Now, we've seen sample declarations of general and static globals in file1.c here. For the static global, that's pretty much the whole story. Once declared as shown, it may be accessed by all functions in the file. But the general global is more complex. When compiling one .c file, the compiler will not examine other .c files. This is a general principle of C compilation. Only one .c file at a time is considered. So a variable is usable in a C source file only if it is declared in that file or in a header file that's included by it. If we want to use a general global variable throughout a multi-file C program, it must be present in every .c file, either directly or by header file inclusion. But we cannot simply repeat the global definition in every .c file. This would imply multiple copies of the global, a different copy for each file, and that would result in a linker error. Instead, a general global variable is defined in only one file. For instance, file1 global in file1.c on line 5 here. In our discussion, let's call this the variable's home file. That term applies only in our course. There's no general term for the concept. Now, in every other .c file that uses the general global, there appears, usually via including a header file with the needed line, an extern declaration of the global, e.g. extern int file1 global as on line 1 of file1.h here. And of course, file1.h is included in both the other .c files of our example here, there and in main. Now, an extern declaration does not create a new global variable. It simply announces the presence of the variable in some other .c file so that we may use it. The machine language translations of such uses from other files, as for instance on line 15 of file 2, are left partially completed to be filled in by the linker when all the object files compiled from various source files, including the variable's home file, are merged into a single executable file. In C and other programming languages, it's useful to differentiate between a definition of a global variable or a function, which is the line that actually creates the variable or the lines that provide the function code in the home file, versus the declaration of a global variable or function, which simply announces the existence of the variable or function in some other file. A declaration allows uses of the variable or function to be checked and partially compiled, with the partial compilation filled in finally by the linker when the home file is linked in. Extern global declarations and function prototypes are declarations, not definitions. And by the way, it's okay to have both an extern declaration and a definition of a global in the same file, as we do in fact for file 1global in file1.c. The compiler will forgive you and ignore the extern in this case. Here's question 2, by the way. Where is the extern declaration of file 1global in file1.c? Coming back from a pause there, it's in the included file 1h, right? So the reason for this forgiveness rule is that it allows a .c file to include its own .h file, which is often useful. Now, another use of the static keyword fits naturally into this discussion. Local variables, such as static local, on line 9 of file 2.c, may be declared as static. This changes their behavior significantly. A normal local variable loses its content between two different calls of the same function. It is, in effect, uninitialized at the start of every function call. But a static local retains its content between function calls. If you put a value into it in one call, that value will still be there on the next function call. In a very real sense, as we'll see in detail later, a static local is like a global variable that can be accessed only within the function that declares it. So it's persistent in value, like a general global or a static global, but it's even more restricted in its use. And one side effect of this restriction is that you must initialize a static local in its declaration, as we do on line 9 here. The initialization occurs just once, not every time the function is called. Indeed, the initialization takes place before the program even runs, right at the very start of it. By contrast, using an ordinary assignment to initialize the static local, by, say, putting it down in the code down here, would reset its value on each function call, eliminating the advantage of being able to retain values from earlier function calls. Now that we have all the basics in place, let's trace the behavior of the main program in our example slide here, following the changes made to the two general globals, file1global and file2global, and the two, not one, static globals, static global in file1.c and static global in file2.c, and then, of course, the static local. First, note the initial values of all 5 variables. There, 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 and finally there. Then check the first line of output here. File 1, or bump file 1 globals to be exact, has incremented both file 1 global and its static global. The result shows in the output. And it also shows that file 1 has access to file 2 global via the extern declaration that it included in file 2.h. Now, in the main, we directly modify file 2 global on line 8. And that shows that main has access to it as well, due to inclusion of an extern declaration in file 2.h. The call now of bump file 2 globals illustrates that file 2 code has access to file 1 global, right there, and file 2 global has value 101 after incrementation because of main's modification. And static local has value 1 incremented from its initial value of 0. Here's question 3, just to be sure you were listening earlier. Why does static global now have value 21? How did that get changed from the 11 on the earlier call? Coming back from a pause there, it didn't get changed. That's a different static global, the one confined to file 2, which was initialized to 20 and just incremented to 21 now. Tracking now the final 2 calls of bump file locals, file 1 globals, and file 2 globals, we can see that the 2 general global variables continue to get updated and used in common between the 2 functions, while the 2 static global variables remain independent of each other. And static local does indeed retain its value between function calls as advertised. So here's a question 4 for you. We've seen in earlier lectures that functions may return pointers to variables. If bump file 2 globals over here returned an int pointer, do you think it would be okay to return the address of static local? What about returning the address of a non-static local variable? Make your best estimate of the answer based on what we've said about these 2 types of locals. Coming back from a pause there, the fact that a non-static local loses its content between function calls suggests that it ceases to exist between calls. And this is true in essence. And the exact fact is that the memory area for a non-static local will be used for other purposes between function calls. Thus, returning a pointer to it is a bad idea, since the pointer's target would be obsolete upon return. But returning a pointer to a static local is fine, since it continues to exist between function calls. Now, you might have answered instead that returning the address of a static local should be forbidden because it permits modification of the static local from outside the function. This would be a reasonable surmise, but in fact C makes no such restriction, so you can get around the restriction on access to a static local by returning a pointer to it. Indeed, it's not uncommon for a function to configure some static local variable and then return a pointer to it for general use by other code.